My name is Holger Hintelmann, and I'm the Interim Vice President Research and Innovation here at Trent University. It is my great pleasure to welcome you tonight here in our Student Center, next to the beautiful swirling waters of the Otonabee River, which the Mississauga call the river that beats like a heart. So how appropriate that it runs through our campus which sits on the treaty and traditional territory of the Mississauga Anishinaabe. We are grateful for the First Nations of this region for sharing their knowledge and working with us to tell their story. On behalf of Trent University, which is celebrating its 60th anniversary this year, it is my honor to welcome you to the annual David Poole Lecture in Mathematics. I'd like to welcome also President Dr. Kathy Bruce, who has an extensive background in mathematics herself and has received many accolades for her research into mathematical learning. Throughout her impressive career in education, President Bruce has focused on exploring productive pathways to learning complex concepts and ideas, particularly in math. So we're delighted to have you here tonight with us, President Bruce. Since its beginning 60 years ago, Trent University has strived to be a strong partner enhancing the community and culture of Peterborough. Sharing knowledge, such as we are doing tonight, is just one of the ways we give back to our community. This lecture, in fact, is part of the university's Community Speaker Series that hosts lectures on a wide variety of topics. And our community, in turn, helps us to enhance the university and the student experience in many ways, including through philanthropy. Significant contributions from the businesses, unions, employees of GE, and many in the Peterborough community helped Trent become a reality in the early 1960s. And the impact and importance of giving is truly appreciated, especially in times of increased financial pressures for many of our students. Tonight's event is thanks to the generosity of Trent University Professor Emeritus Dr. David Poole. Dr. Poole is the former chair of Trent's Department of Mathematics and a former Associate Dean of Arts and Science. During his long, illustrious career, he won the highest teaching awards that are given from Trent, the province of Ontario in Canada, and was also named a Fellow of the Canadian Mathematical Society. Dr. Poole established his annual lecture series to share his passion for high-quality teaching as mathematics with students, faculty, and the community. On behalf of Trent University and the Peterborough community, thank you, Dr. Poole, for your vision and dedication and for the legacy you have left to our university. So I now welcome Dr. Poole to the stage for some brief remarks and to introduce our tonight's speaker. David.
Thank you, Holger. And welcome, everybody. Thanks for coming. A few words of thank you that I need to make. An event like this one doesn't happen on its own. It takes a dedicated group of people working hard to pull it off. And so I think I want to name some of those people and thank them personally. Colleen Berrigan, who tirelessly looks after a lot of the logistics for this event, making travel and accommodation arrangements. Babin Joy and the entire AV team, people like Don back there, do an amazing job of recording events like this and making them available to people online afterwards. And last but not least, I want to thank Emily Vasiliadis, who oversees the entire project. It runs incredibly smoothly, thanks in no small part to Emily's leadership. I know there's other people who have been involved. I may not have met you, or we may not have spoken, but I thank everybody who's involved in organizing tonight's event. It's now my pleasure to introduce tonight's speaker, Dr. Gerda de Vries. Gerda received her bachelor's degree from the University of Waterloo and her doctorate from the University of British Columbia. She joined the University of Alberta in 1998, and she's currently a full professor in mathematics and statistical sciences. She also serves as Associate Dean for the Faculty of Science at U of A. Gerda's research lies at the interface of mathematics and biology. Her research interests include dynamical systems on the math side, and she's interested in applications to cell biology and neurophysiology. She's also the co-author of a 2006 textbook, A Course in Mathematical Biology, and she served as president of the Society for Mathematical Biology from 2011 to 2013. She became a fellow of that society in 2017. Gerda is a passionate advocate for interdisciplinary education and has worked tirelessly promoting science in the schools and providing support for women in mathematics across Canada. She's the recipient of many awards for excellence in both undergraduate teaching and graduate student mentorship. I want to mention a few of these. Bear with me, this is a long list. She received 2004 Faculty of Science Award for Excellence in Teaching from the University of Alberta, the 2006 Rutherford Award for Excellence in Undergraduate Teaching, also from U of A, the 2009 Education Prize from the Pacific Institute for the Mathematical Sciences, PIMS, and the 2014 Excellence in Teaching Award from the Canadian Mathematical Society. Gerda was named a Fellow of the Canadian Mathematical Society in 2018. She's a highly sought-after public speaker, giving lectures on the importance and the joy of mathematics. She's also a self-taught and very accomplished quilter and is able to weave, pun very much intended, to weave her love of quilts and mathematics together, as we will experience tonight. We know that you will be inspired, enlightened, and delighted as Gerda shares the mathematical stories behind a variety of both traditional and contemporary quilts. Her talk is entitled, Making Mathematics with Needle and Thread. Gerda, over to you.
Thank you, David, for your kind introductions and for for instigating this visit to Peterborough and Trent University. It's been a delightful visit so far, and I'm really overjoyed to give this talk. Whenever I can give this talk, I'm happy because it just gives me joy, and I know it gives the audience joy as well. That's my aim, anyways, is for all of you to leave tonight with a smile on your face and having learned some new mathematics, perhaps, and certainly learned about the possibilities of mathematics in art. Now, I happen to talk about quilting, but you can imagine that exactly the same thing could be true with woodworking, with weaving, with knitting, et cetera, et cetera. So there's anyway. So this is a poem written by a dear friend of mine that I thought is a really great way to start the talk. So what's in a quilt? Small squares and triangles waiting to be built into larger rectangles to be sewn in pairs so that all the angles make one large square to hang on a wall over perpendicular stairs. And so there's already so many mathematical words in there that it's just fun. And these two pictures are pictures of me when I was 3 years old. So I grew up in a family where doing things with your hands was all the time. We never had idle hands except for on Sundays, perhaps. But my grandmother taught me to knit when I was about 6 years old. I was clearly interested in sewing when I was 3 years old. I'm actually standing up here because otherwise I couldn't reach the foot pedal. And my job as a 3-year-old was to iron my dad's handkerchief. So I'm sitting there with a very hot iron. I don't think parents are allowed to do that anymore these days. But anyways, all right, now we get to test the forward. Oh, look at that. Okay, there's the title of my talk. And first of all, I just want to make sure that we all know what a quilt is. So just to be on the safe side. So a quilt really is it consists of 2 layers of cloth. So here I've got 2 layers of cloth, 2 layers of fabric, and they are layered with a piece of wadding or batting is what we call it. You put that in between the 2 pieces of cloth. Now you stitch the 3 pieces of fabric together or of textiles together, and that is the process of quilting, is actually putting a needle and a thread through these 3 layers. You could also tie it. You could also put pieces of wool through here and then tying it with a knot. That's also called quilting. Basically, you need something to keep these 3 pieces from not coming apart. So that's what a quilt is. Now, quilting has been done all across the world for centuries, longer than centuries. And so here are 2 examples of how people used quilts to keep themselves warm, and for protection as well. So on the left is a skirt that dates back to the 1700s. It would be a nice warm skirt that you would wear in the winter, perhaps as an underskirt, and then you would put something more fancy over top of it. On the right-hand side is a coat that was worn by knights under their armor. So that was just an extra layer of protection in case something sharp came through the armor. That was so warmth, protection. These days, when we think of quilts, we typically think of these 2-dimensional objects, mostly blankets or throws that you put on a couch or something like that. And more recently, people also use hang quilts on walls. So you can put a bed quilt on a wall if you really like it, or something smaller, right? And you can imagine that there's all kinds of stuff that you can now do. And so I just want to highlight 3 types of quilts. All of these are quilts. Now, the one on the left-hand side is just actually 1 piece of cloth on the top, and the feature there is the quilting, right? So the quilting there is what makes it creates the interest. It makes the vines and the flowers and things like that. Sometimes what people do is they put some extra filling so that the leaves really pop out. It really becomes a 3-dimensional object then. Most people think of quilts, the example that's in the middle. You cut a whole bunch of small pieces of fabric and you sew them together. So typically squares, triangles, and things like that. So we call that a pieced quilt. Where the piecing only really refers to the top layer of the quilt. And then there's also applique quilts. And applique quilts, you start with 1 piece of fabric and you sew little pieces of fabric on top of it. Okay, so you either attach pieces of fabrics or you put fabrics on top. Okay, so that's kind of in a nutshell what a quilt is. And then if you're really sticky about it, a quilt isn't really a quilt until you finish it. So here's an example of it's just a pot holder. Many of you, I think pretty much everybody has a quilt at home. So this is also a quilt, happens to be a pot holder, but we put binding on top of it so that things don't fray. Okay, so there are people who say it's not a quilt until it's finished, until you've bound it. Okay. All right, so now we all know what a quilt is, and now what does mathematics have to do with a quilt? Well, of course, every quilt has dimensions, right? So right away, we can think about things that way. You can also think about the geometry of fitting squares and triangles together, but I want to go beyond that, right? I want to talk about all kinds of interesting mathematical concepts that you can visualize in quilts, or when you have a quilt, maybe we can use mathematics to dissect that quilt and use mathematics to understand the quilt. Okay, so I'm hoping I have enough time to touch on all of these topics. It may be that I have to cut something out towards the very end. It was already difficult to bring all of my slides down to this small collection. I think in the Over the years, as I've been developing this talk, I've collected so many stories and so many pictures that I have probably enough now to write a book. And maybe at some point that will come, but I could easily fill 3-4 hours, just keep going. But I know I only have an hour of your time, and I think that you will want to go to dinner at some point. So we will stop at 6:15. But without further ado, let's take a look at the first topic. So I'm going to start with a fun one, which is the Möbius band. So a Möbius band is a topological object. Actually, let me put down it's a topological object with only one side and one edge. Topology is a branch of mathematics that studies the properties of objects when they are transformed continuously. So by a deformation such as bending or stretching without cutting or punching holes in it or something along those lines, right? And so a Möbius band is a really curious object. And so the way that you would construct a Möbius band is as follows. So first of all, here I've got just a rectangle. I think all of you would agree that it has two sides. Let's just forget about the thickness, this little thing. You could think of that as a third side, but or a third dimension, but we have two dimensions really here. We have two sides, right? Front and the back, and two edges. Let's forget about these two little edges because I'm going to join them, okay? So if I join them like this, I have an inside, and I have an outside, and I have a top and a bottom. Everybody agree with that? Okay. Now, if I, instead of joining them this way, I join them this way, I get a Möbius band. And so all of a sudden, I no longer have an inside and an outside. I just have one side. If I start painting this side, I keep going, I keep going, and I keep going, and I keep going, and I end up where I started. So it actually turns out to be just one side. I can't paint this with two colors. I have to keep going. And the same thing with this side. This side is one continuous side. It just kind of keeps going. Anyways, keeps going, ends up on the green side, and ends back up on the white side. So one side and one edge. And a Möbius band has really interesting properties. So here's I've glued things together. So here's the Möbius band again. If you cut a Möbius band in three, or let's say that differently. If I put a line 1/3 away from the edge, right, I actually end up connecting. I end up. Yeah, I said that differently. Then I said that incorrectly. If I cut on the line that is 1/3 away from the edge, let me say it that way, then you end up you keep cutting and you keep cutting, and you end up with this. You end up with a small loop that itself is a Möbius band, and you end up with a long loop that has two twists in it. It's this kind of stuff that's really interesting to mathematicians. And so let's take a look at what people have done with that in quilts. So here's somebody who's made a table runner, but it's not really a runner, it's a table loop, right? It's a decoration that you can put on a festive table. This maker has also done something fun with the hands. The hands just kind of rotate as you go around the Möbius band, and then when the hand comes back to where they started, you have a left and a right hand meeting. That's kind of fun. Here's a quilter who has put zippers in their Möbius band 1/3 away from the side, and so this quilter can unzip their Möbius band and end up with this construction over here. It's kind of clever. And then here's an individual who has, this is actually a really fun title. The title of her work is Life is What Happens When You Were Planning Other Things. And so sometimes life gets messy. Well, same thing with quilts, they sometimes get messy. And so it's actually this object. It's the small Möbius band and the long loop with the two twists that have been nicely arranged in a little heap. Okay. Oops. And here is a beautiful interpretation of the Möbius band as well. This is a recent quilt by an artist named Audrey Essaray. And she's named this the Möbius radial quilt. She actually sells these patterns. So if you go to her website, you just type in Audrey Essaray and it'll come up. And unbelievably precise quilter. It's hard to do these really narrow bands and to do this in a circular array. Like this is the technical skill involved here is really quite something. And I think visually it's very, very striking. Yeah. So if you go to her website, you'll see. I mean, clearly she's got a mathematics interest as well. A lot of her quilts have, they're interesting to mathematicians. All right. So that was just a fun introduction to how mathematics can infuse quilting and how quilting can infuse mathematics, I think. Now, let's take a look at a little bit more academic study of quilts through symmetry. I think we all have a good idea about what symmetry means. Symmetry is when we've got repetition in an ordered way. And when you were in elementary school, I'm sure that you've played around with the ideas of symmetry. So in mathematics, we know that there are 4 symmetry operators. And I'm going to show all 4 to you and then explore what you can do with that and to create bigger pattern. So the simplest symmetry operator is translation. And so I've created a asymmetrical quilting block, which is the left square, and I've put a purple square in there and a blue shape, blue quadrilateral. And I made it purposely asymmetric, that quilt, because that will make it more easy to see what happens when we apply these symmetry operators. And so translation simply means let's just move the block over. Okay, that's all it means. You can move it diagonally, you can move it to the left, you can move it to the right, but that's a translation. Translation just means move. Another operation, symmetry operator, is reflection. So here I've put a mirror, or imagine that you put a mirror on the solid black line, the thick black line that is in the middle. And if you put a mirror there and you flip it over the mirror, essentially, then that's called reflection. Okay. Rotation is another one that many of you will be very familiar with. So imagine putting a pin where I put that big black dot. And now you can just rotate that block 90 degrees and end up with the square on the right-hand side. You could put the pin in a different spot. I could put the pin over here as well and rotate around that particular point, right? So but that would also be called a rotation. And then there is a 4th symmetry operator that's a really tricky one, and that involves a reflection and a translation at the same time in a particular way. So the way to show you that is focus on the left square and focus on the horizontal bolded line. And I'm going to flip the block over that horizontal line. So now the purple square is at the bottom and the blue quadrilateral is at the top. And now I'm going to move or translate that result in the same direction as the horizontal line. So because horizontally, with other words, because I did the flip horizontally, I have to move horizontally. Okay, and that's called a glide reflection. Now, how can I create pattern with these 4 symmetry operators? So let me show you that on the next slide. So here, We start with that same block that I had on the previous page, but I've made it a lot smaller, and I just translated it over and over and over again, okay? Don't worry yet about the gray shaded area and the orange outline. That'll come in just a second, okay? So that's kind of maybe a little bit of a boring pattern, but you can imagine that this can go on forever and ever, and you can make a wallpaper pattern with that. If your original block had maybe a little bit more interesting design, then you might have an interesting wallpaper. Okay, here I've started with the original block, highlighted in gray. We'll call that a cell, and a cell I'm going to define as the smallest unit that is repeated. Okay, and the orange outline, let's call that a tile, and that is the smallest unit in a pattern that is repeated through translation. Okay, and so here I've basically created a tile by rotation. So there's the rotation the rotation operator has been used in there. And the point of rotation is right in the middle of that orange outline. And so you can see that I started with the block, rotated at 90 degrees, rotate 90 degrees, rotate 90 degrees. Okay, and that that tile has been repeated by translation. Okay, it's a much more interesting pattern, I think. It actually turns out that quilters use this pattern a lot. All right, now you can create lots of other patterns. So, So here are 4 other patterns that you can create by choosing the size of your tile and choosing the symmetry operators that you're going to use. So now you could ask the question, and this is a question that mathematicians would ask, in how many ways can you do this? Right? And the answer is actually quite surprising. Exactly 17 ways. Not an infinite number of ways, not the 6 ways that I've shown you, 17 ways. Well, now, if it's only 17, then they all need names, right? So here is the 17 ways. So here, instead of the block that I've used, the person that made this picture used a hand. And so here's all 17 ways that you can put that together if your hands are on a square, or if they're on a diamond or an equilateral triangle or something along this way. These are the only ways that you can put that together in a regular way. Right? There's other ways you can put this together, but then you can't repeat it forever and ever. And the idea here is that if we want to make wallpaper, you have to keep doing this forever and ever. So then there's only 17 ways. And then you've got these really cryptic names. So there's not going to be a test. But they do have really cryptic names. Now, of these 17 symmetry groups, there are 4 that I use regularly by quilters. There are some that are just rarely used by quilters. Here are those 6 patterns that I had shown you before, but now identified by their group name. So P1, P4, PM, M stands for mirror, so there was a reflection that took place there. P2MM has 2 reflections, et cetera, et cetera. PG has a glide reflection in it, and P2GG I think has 2 glide. Anyways, there's some rhyme or reason to the naming of these patterns, but it's not obvious. All right, now let's dissect a quilt in terms of symmetry. But before I dissect it in terms of symmetry, let's first of all think about how would a quilter make this quilt. So I actually made this quilt, so I know how this is made. And so a quilter would make blocks. They would make squares. And there are 2 types of squares that make up this quilt. There is the star quilt, the star block that I've highlighted here in white. And there are those connecting blocks that I've highlighted in yellow. Okay, so when I made this quilt, first of all, I made all of the stars, and then I laid them out on the wall. And then I made the connecting blocks, mostly because they needed to connect to the neighboring stars together. They needed to repeat some of the fabric from the stars, and so I could only make the connecting blocks once I had figured out what the configuration was of the stars. Okay, so that's how a quilter would look at this quilt, but not a mathematician. A mathematician would want to know, what is the tile here? What is the smallest unit that is repeated by translation? And it turns out to be these squares, but the squares are on point. Okay, that's the smallest unit that is repeated by translation. And then within that white tile, what is the smallest unit that is repeated by the symmetry operators? And it's these, oh, sorry, that's I forgot about that one. It's all of these little triangles. Okay, so one tile consists of 8 little triangles, and that little triangle, that's the unit, that's the cell, that's the smallest element that is repeated through the symmetry operators. And now that we've figured this out, now we can identify what the symmetry group is, and it turns out to be the P4MM symmetry group. Okay? Just because we know it's P4MM doesn't tell us anything about what a quilt would look like, because here are 2 other examples of quilts in exactly the same group, and they look very, very different, right? The quilt on the left is the quilt made by Ruth McDowell, and I know that there are quilters in the room, and I see people nodding their head. I think that means you know of the name Ruth McDowell, and maybe you've taken a workshop from her, but she's an absolute master quilter. The reason I like Ruth McDowell so much is Ruth McDowell has a background in engineering and architecture before she turned to quilting and made quilting her full-time job. And it's actually interesting. She went to a quilting show early in her quilting career, and she noticed that there was a man studying all of the quilts and making all kinds of notes. And she went up to this individual and I said, "What are you doing?" And he was a mathematician, and he was trying to figure out what all of the groups were of all the quilts. He said, "Do you know that you keep using the same symmetry groups over and over again?" So she said, "Tell me more about these symmetry groups." So she then learned about the 17 symmetry groups, and then did exactly the opposite and made an example for each symmetry group. So she has a book on symmetry. I need to find the exact title if you're interested, but if you search on it, I'm sure you can find it. And so she has a chapter for each symmetry group with examples of quilts. So she said some quilts were, or some symmetry groups were easier than others. So the mathematics definitely inspired her to explore the different symmetry groups. And the quilt on the right is made by me. I brought a few quilts with me. This is a really nice one to show in person. It's about this big square. But my suitcase was only so big, so unfortunately I could not bring this one. All right, so that was an analytical treatment of quilts. Now let's flip again. Let's go back and let's kind of see what quilts have been inspired by mathematics, and what mathematical concepts have been used to make interesting looking quilts. And so when I ask, where do you think mathematics might come in? And once we get beyond how do you fit rectangles and squares together? Once we get beyond that, a lot of people come up with, is there anything you can do with pi? And it turns out there's lots of things you can do with pi. So first of all, what is the number pi? So just a quick review, that pi is the ratio of the circumference to the diameter of any circle. The number pi was known for thousands of years already by mathematicians. It's an irrational number, so if you write down the decimal expansion of pi, it goes on forever. Okay, and some mathematicians, they have actually not just mathematicians, people like to memorize lots of digits for pi, and sometimes on pi, especially on Pi Day, which is March 14th. It's March 14th because 3/14, March, the third month, March 14th. That's why March 14th is Pi Day. And so on Pi Day, you often have contests for who knows the most digits in the decimal expansion of pi. I only know 3.14159. It's as far as I go. All right, so that's the number pi. Now, here are two quilts inspired by the number pi. The first one, I think, is really nice to put in a mathematician's kitchen. It's apple pie. There's the fabric that's been used to make the symbol pi is apple fabric, so apple pie. I think that so unfortunately, these two images were collected years ago, and I don't have a high quality image, and they no longer are on the internet. I can't reach the makers of these quilts to get higher images, higher resolution images. But I think you get the idea that the second quilt, I think, is a really nice quilt for a mathematician's office. It has a mathematical treatment of pi, the geometry, the history of pi, and it's all worked into the quilt. And then here's a really abstract representation of pi. And I found that when I was doing research on pies and quilts, I came across this quilt, and the name of the quilt is Pie Sans Salt and Pepper, made by an artist named John Sims, who was also a mathematician. And I kind of went, why, where is pi, right? And digging a little bit further, I found an article in Science News that explained where pi is. So here are lots of the digits in pi, so 3.14159, et cetera, et cetera. And what John Sims did is he attached a color to each of the numbers. So 1 is brown, 2 is, I think, blue, 4 is red, et cetera, et cetera. And then he put pi on a rectangular grid. And so I'm going to focus on the 6x6 square that I have highlighted in white. Okay, here is that same 6x6 square. And once you've got all the numbers in there, then you can color them, right? So then all the 1s are brown, all the 4s are like a yellowish mustard color, the 3s are red, et cetera, and you end up with this particular quilt. Now, he did this for years. So he was he brought for every year for Pi Day, he brought a new quilt into the classroom, made with this concept. And so what do the other quilts look like? Well, here's another one from a different year. You can recognize that the middle is exactly what we just looked at. It's just a smaller version of it, right? Basically just a center of what we just looked at. And then the other two, well, this is really cool. He represented pi in base 3 and base 2. And so if you represent pi in base 3, you only use the digits 0, 1, and 2. And you can actually go into Google and say, what is pi in base 3? And out pops 1, 0.01, et cetera, et cetera, et cetera. And there it is. So we start at exactly the same point, the one that is highlighted in the middle there with a bold black line. And again, you follow that spiral around and use 0 for blue. So blue for 0, red for 1, and white for 2s. And then you end up with the top right-hand corner in the quilt. The bottom left corner is also pi base 3 with using different colors. And then pi base 2 is the other two corners of the quilt. But you can see that what happens if you have pi base 2, you only use 0s and 1s. And so 2 colors will suffice. And he used black and white for one and white and black for the other. And so the 2 corners are exactly opposite coloring. Okay. So there it goes. Isn't that fun? And so then here's a few of his other quilts. So he's done the original coloring with just more digits. The middle one is base 3, and the one on the right is base 2 with just lots more digits. Okay, so this kept him going for years. It's really quite fun. All right, this is a really interesting story. Is there? Actually, I should ask, how many mathematicians are in the room? Okay, how many quilters are in the room? Okay, anybody math and quilter? Yay! Oh, yay! So, are there mathematicians who know what projective planes are? Yes? 2? Okay, so if I'm saying anything incorrect, can you tell me after the lecture? Because I'm an applied mathematician, and all I know about projective planes is what I'm going to tell you now. Okay, so how did I become interested in projective planes? Well, it's because I saw a quilt with the title Projective Plane of Order 4, and that to me screamed mathematics, right? And so the way I came across this quilt is that I gave a version of this talk at McGill University several years ago, and after my talk had been announced in Montreal, a woman named Lily Lamb contacted me. She emailed me. She said, Gerda, I'm also a quilter. I also have a background in mathematics, and I look forward to meeting you. Kind of, okay, let's Google her, right? And this quilt came up. And so then I kind of went, wait, I need to know. So I asked Lily, can you please explain to me how this quilt came about? So I got an email message. I don't know how many pages it was, right? And so I studied that, and this is what I can tell you. So first of all, a projective plane of order n is a geometry in which each point has n plus 1 lines on it, and each line has n plus 1 points in it. Okay, just hold on to that thought for just a bit, right? And so what do mathematicians do with this? What is the question that mathematicians might ask? They might ask, does a projective plane of order n, you choose n, 5, 6, 10, 20, whatever, does it exist? Okay? So one could ask the question, does a projective plane of order 2, does it exist? And the answer to that question is yes, because we're looking at it. Okay, so a projective plane, or looking at a visual representation of it, a projective plane of order 2, you need to have each point has to have 3 lines on it, and each line has to have 3 points on it by this definition. Okay, so if you look at each point, let's look at the top vertex, for example. Does it have 3 lines on it? Yeah. Okay, it has 3 lines on it. Let's look at a point kind of on the left side, in the middle of the left side. Does it have 3 lines? Yes, it has the edge on it. It has the circle on it, that's the second line, and it has the diagonal on it, that's the third line. Okay, so each point has 3 lines on it. Now, does each line have 3 points on it? Looks like it. So the left side, for example, has 3 points on it. Okay, same with the bottom and the right side, of course. Does the circle have 3 points on it? Yep, has 3 points on it. Does each diagonal have 3 points? Yep, has 3 points. Oh. Each line has 3 points on it. Each point has 3 lines on it. That means it's a plane of order 2, projective plane of order 2. What does this have to do with Lily Lamb? Well, Lily Lamb happens to be married to Clement Lamb, and Clement Lamb is a mathematician, and his claim to fame is to prove that a projective plane of order 10 does not exist. Okay, so that's how Lily knows about projective planes, and Clement asked Lily to make a quilt for his office, and she had no choice but to make a quilt on projective planes, and so she represented a projective plane of order 4, and the quilt that we just saw earlier was the result of that. So now, how does that work? So we have to make a little bit of a leap of faith. So a projective plane of order 4 is related to 3 Latin squares. A Latin square is like a Sudoku puzzle. Okay, but it's a Sudoku. So here our Latin square is 4 by 4, whereas Sudoku puzzle is 9 by 9. Okay, so that means that the numbers 1 through 4 appear over and over again, but each number can only appear once in every horizontal line and only once in every vertical line. Okay, so you can fill in the numbers lots of different ways. Here's 3 ways that you can do that. So here are 3 Latin squares with the numbers 1 and 4. And the property of these 3 particular ones is that they're mutually orthogonal. Now, what does it mean for 2 squares? People are laughing. Am I doing well so far? Yes? So what does it mean for 2 Latin squares to be orthogonal? Imagine that you slide 2 of them on top of each other, okay? And then you read the numbers that are sitting on top of each other. You need to see every combination exactly once. So 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, etc., right? So there's 16 combinations. And you can check. If you put the first one and the second one on top of each other, you see that exactly. You see every combination exactly once. There's none missing. There's no doubles. The same thing if you put the first and the third on top of each other, and if you put the second and the third on top of each other. That's what it means for these 3 Latin squares to be mutually orthogonal. Okay, so now we've got, and I haven't told you anything about the colors yet. So now you can because the top lines are 1, 2, 3, 4, that means in a column that starts with a 1 at the top, there are no other ones. Okay, so if you collect the 3 columns, the first 3 columns from each square, you end up with a collection of 2s, 3s, and 4s. Okay, so that's exactly what I've done. I've collected all the green columns together and I've glued them together. And represented at the top left diagram at the bottom. You can do the same thing with the second column, the purple ones. Okay, so you can see how all the numbers kind of move in the right spot. Okay, and so then what Lily did is, so now you can start seeing a quilt, right? And what Lily did and then is did a color numbering. So this is only for me, the coloring that I've done so far is only to move the numbers in the right spots. Now I'm going to, Lily, color all the 2s a particular color, all the 1s a particular color, etc., etc. And the easiest way to do that is to say, you know what, let's make all the 1s green. All the 2s, all the 2s purple, all the 3s, I don't know, whatever color that is, and all the 4s turquoise, and then you end up with that, okay? Minus the stuff that I've got in the middle. Okay, so if you look at the numbers have moved over exactly the same way that they are shown on the left, but now they're colored using this particular map. Okay, and then Lily thought that, well, rather than just gluing all of those squares together with the numbers, let's separate them. And so what she's done is she's bordered the first one with green because there are no greens inside there, right? Because there were no 1s in there, right? And then in the middle, she's got a hodgepodge of colors kind of to tie everything together in an opposite way. So there it is. Super satisfying to discover the story behind this quilt, right? Now, I mean, at first it was curiosity. How come the quilt with this title, projective plane of order 4, how does that come about? Well, now it comes about, and just learning that and figuring it all out gave me joy, and hopefully it has given you joy as well. All right. So mathematical puzzles. I mentioned Sudoku earlier, and the idea of using color, or using a color map, right? Turning 1s into reds, or turning 2s into blues, for example. Well, you can imagine, you can do the same thing with a Sudoku puzzle, right? And somebody has made a business out of this. Okay, so there's a whole book on Sudoku quilts. So you can go beyond using a color map. You can actually use a pattern map as well, right? And here, this person on the cover of this book has used a very well-known pattern, square and a square, and so it's just that the outer fabrics and the inner fabrics would represent a particular number. That color choices. So, and here's a lady who's made a whole series of Sudoku quilts. The one on the left is called Underwater Sudoku. So the fabrics used are shimmering water type of patterns. The one in the middle is called Sudoku on Vacation. So some safari fabrics. And the one on the left is called Sudoku Madness. And I can just imagine that it was a really hard Sudoku to solve, and wanted to preserve it in fabric. Okay. So here is a mathematical puzzle of a very different type that has generated a really interesting quilt that I will show you in just a second. Most people start talking about triangles, right? Wanting to put diagonal lines in there, but the triangles are not the same size when you do that, so they're not 4 equal parts. And so this is indeed the answer. I think this is what you were trying to describe. Yeah, so you can put 4 smaller L's of exactly the same, each of exactly the same size inside the bigger L, okay? And here is how that mathematical puzzle has been interpreted in a quilt. And I just love this quilt on so many different dimensions. I love the fact that it's the visual representation of an answer to a mathematical puzzle, but it's also on different scales, right? And it's not just one scale, it's 2 different scales. Let's take a look at the golden ratio. Okay, the golden ratio is another famous number like pi. And it's represented by the Greek letter phi. I've got 2 different symbols here for phi. So there's the circle with a slash through it, and then there's the descriptive version of it, but they're both the same symbol, or sorry, different symbols for the same number, phi. And the way to represent this particular ratio, the easiest, is to show this geometry. So it's the geometry of a very particular rectangle, where if you take away a square from that rectangle, you're left with a smaller rectangle that has exactly the same ratio of short to long side. So in mathematical terminology, it's a rectangle that is similar to the larger one. So if you expand the smaller one, you blow it up, you get exactly the bigger rectangle on the left. Okay, so the ratio of the short side to the long side of those 2 rectangles is exactly the same. So you can set up an equation. So 1 to phi from the left rectangle is the same as phi minus 1 is to 1. Okay, so then you can set that equation, you can cross multiply, get a quadratic equation, solve for it, and you get phi is equal to, you need to take the positive answer, not the negative answer, so you get 1 plus the square root of 5 divided by 2. That's phi, okay? Turns out that phi shows up frequently in very unexpected ways in geometry, okay? And one way in particular where it shows up in abundance is in a regular pentagon. Okay, so a regular pentagon is a pentagon with 5 sides, where the 5 sides have equal length, and the interior angles are exactly the same as well. That's what's meant by a regular pentagon. And then if you make one side length phi, then that horizontal diagonal is phi squared. That little piece in the middle is 1 divided by phi. And the vertical diagonal, which is it's actually this. So you can divide any of the diagonals into a piece 1 and phi. So phi shows up in many different ways. Okay, and that's called the lute of Pythagoras. And then you do a little bit more mathematics, and you realize that the angle of that lute, that interior angle, is exactly 36 degrees. Well, we've got 360 degrees in a circle. That means you can put 10 lutes in a circle. And that's what this lady has done. Has turned the lute of Pythagoras into a quilt. Okay? She's called it the golden ratio. Could have called it lute of Pythagoras. It doesn't matter, right? It's just it's a gorgeous quilt. And so if you're just wondering where is that lute, there it is. There's one of the lutes. But she's also done some really interesting things on the outside, and there's different versions, smaller versions of the lutes sitting right there. Isn't that cool? It's not just a quilt with a bunch of stars, right? There's way more in there. And then, of course, the color choice, all the golden fabrics, is just lovely. So I think this is another lovely, lovely quilt with a lovely mathematical story. Okay. This is more lute of Pythagoras. So there is the lute, but here the coloring is unexpected, right? So here somebody has done some very clever coloring. This is a pattern. I have not seen this executed yet. Okay, so maybe someday when I'm retired, I think I need to make this. Yeah, I think it would be, well, at some point, what do you do in the middle, right? Because these tiny, tiny, tiny little pieces, but they've solved it a very interesting way here. They've just put basically a little flower in the middle. Because at some point you have to stop. At some point you have to stop. You can't make your pieces any smaller. Okay. All right. You want to hear a little bit about fractals? Okay. So first of all, what is it? What is a fractal? So a fractal is a geometric object that is self-similar, and that means that that you can look at it at very different scales. You can zoom in, or you can zoom out, and you start seeing the same things over and over again. There's different ways to generate fractals. An easy way to understand, an easy way to generate fractals, there's an easy one to understand, an easy one for me to explain, is called an iterated function system. And here's an example of that in the picture below. So here's a visualization of something called the Cantor set. So the way to generate that is you start with a line and you remove the middle part, the middle third. Okay? So now the middle third is gone, but you still have these other thirds on the outside. So you do exactly the same thing over there. From each of those, you remove the middle third. Well, now you've got 4 pieces left. You could keep doing the same thing over and over and over again. And eventually, what are you left with? Eventually, it feels like you're just kind of left with dust, Cantor dust. Okay, you've an infinite number of points, but that take up no space. It's really counterintuitive. It's the kind of stuff that you can say, it's weird, it's frustrating, or it's weird, but it's also really cool. It's a really cool, paradoxical, mathematical thing that happens that fires people's mathematicians' brains. It's really quite fun. So you can do this in 2 dimensions as well. And then you get the Sierpinski carpet. Okay? So you start with a square. You cut the square into 9 equal smaller squares. And you remove the middle one. That's exactly the same as what we just did. Whoops. We did over here. I'm going forward instead of backwards. How do I go back here? I found the backwards button. It's exactly the same that we did here in 1 dimension, right? And so now, if you remove the middle one, then you've got 8 squares left, and you can do exactly the same. Each one of those you can divide into 9 parts and remove the middle one, right? And so you can keep going forever and ever and ever, and you end up with a space that, an object that takes up no space but has infinite boundary. Bizarre stuff, okay? And I've translated this into a quilt, and I brought this one with me. So here's the picture of it. And so it isn't exactly a Sierpinski carpet, but it's I think an artistic interpretation of it. I didn't like keeping the middle piece kind of empty. I suppose it would be an interesting challenge is to create a quilt with a whole bunch of holes in it, but but I think technically it'd be very difficult to do. And so I could fill it with I don't know, one single fabric or something like that, but then that takes up too much space, and there's this dead spot in the middle. And so I've chosen to fill the empty spaces with smaller versions of the Sierpinski. So this was the empty space, but I've just filled it in with just different colors. And I think this is a fun combination of, or it's inspired by Piet Mondriaan's coloring. Piet Mondriaan is a Dutch painter, well known for using primary colors towards the end of his career. And Sierpinski. And then I started looking at when did Mondriaan live and when did Sierpinski live, and they were actually contemporaries. Sierpinski from Poland and Mondriaan from the Netherlands. And I'm just you can imagine what would have happened if they had met, right? And so I called this quilt Sierpinski meets Mondriaan. Or Mondriaan meets Sierpinski. Actually, I don't even know which one. Oh, I don't have a label on this quilt. That's terrible. What do I call it here? Sierpinski meets Mondriaan. So it's one or the other. Right. Now, a few years ago, I hosted a graduate student. She was a visiting graduate student from Brazil and lived in my basement for 4 months. And Flora was really interested in learning to sew and learning to quilt. So I taught her, during those 4 months, I taught her how to sew and how to quilt. And when she was gone, she made this back at home, and she sent this to me as a gift. And so she's, this is actually quite amazing. So, because her points are matching perfectly. So she's made a three-dimensional version of the Sierpinski carpet. I'm sure it has a name, but it has escaped me what this version with equilateral triangles instead of with squares, what that's called. But it's a nice little Christmas decoration. And now I have 7 minutes left. Oops. So I'm going backward. So for the quilters amongst us, you're very familiar with the snail's trail block, and really that's a fractal. So the way a quilter builds up a snail's trail is they start with a square and they keep adding on triangles, and then the coloring will turn into a snail's trail. Mathematically, you start with a square and you put a smaller square inside on point by joining the middles. The middle points of the edge, and you keep doing that, and you can keep doing that forever, and you can go out forever, right? So it really is that drawing on the left is really a fractal, and then by coloring it a certain way, you get the picture on the right. The Pythagoras tree is a fractal as well. So here you start with a square. You build an isosceles right triangle on top of it. Is sort of like, think about that as the roof. And then on top of the roof, you put little squares. And you keep repeating that over and over again. And the reason I want to show this is Ruth McDowell has made this quilt. Here she is again. And what's really interesting is that she put the Pythagoras tree on top of a background of a snail's trail. So double fractal. As far as when I look at this, I see 2 fractals. And of course, her color use is spectacular. Okay. Also done by Ruth McDowell, she saw the noonday lily block. And if you focus just on the top left square, you see that in the pink, you see a bunch of right angles. And kind of, wait a minute, you can put smaller versions of that same block in there. And so there's her quilt. So the noonday lily block goes fractal. And she's done about 4 iterations of this. And at the very end, she just sewed in the last one because, again, the pieces of fabric become too small. Okay. I'm going to skip a couple of slides. Okay. Just don't go, oh, no. Because I want to show you my last few quilts. I want to show you a little bit about, give you a little bit of insight onto how my brain works and the kinds of quilts that I like to design. And so here's this is actually the very, it's the third quilt I ever made. And I bought, this was, I bought these fabrics while I was interviewing for a position at the University of Alberta. I was still living in Washington, D.C., and I walked by a quilt shop, and I come, oh, this is really cool. And I bought 5 fabrics, 5 animal print fabrics. And I came back to Washington, D.C., and I kind of went, okay, I want to maximize the use of these fabrics. And I have made this funny design of this quilt block. And I thought, okay, I'm going to use 2 fabrics in each flower. Well, how many different combinations can you make? You can use 5 fabrics for the outside, but the inside had to be different. So I have 4 choices to put on the inside. So 5 times 4 is 20 blocks. So I made 20 blocks using all the different combinations. So these are all different coloring. There's never the same combination of fabrics. And then I could not sew these 20 blocks together randomly. I had to figure out, is there a way to put these blocks so that in one vertical row, none of the outside repeats, none of the inside repeats? I calculated the ways that you can do this, and there's really only 2 ways to do it. And it's just a little game that I play inside my head, because that's what mathematicians do, right? They make rules and they try to follow them. And anyways, but I know that there are many of you in the audience who think exactly the same way. And you didn't realize that what you were doing is thinking mathematically. But it's just, so you may not have a math degree, but you're doing this anyways. And I think that's the fun part. So here's another example. I designed this block. I designed this triangular block, and I split it into 8 tapering strips. Okay, and then you can create the asymmetrical partner that I've put at the bottom there, and then I've labeled the strips A, B, A, C, A, B, A, B. Don't ask me why I did that, but I've stuck with this coloring because I'm not done exploring this particular coloring yet, or this particular labeling. And then you can use 3 colors of fabric. So you choose 1 color fabric for A, 1 color for B, and 1 color for C, and see what you can do. Well, here's the first quilt that I made. Okay, so first of all, of course, I choose what fabrics I put for A, B, and C, and then I decide, I make up rules for how do I put triangles together, right? So the triangles with their asymmetrical partners, and then I make rules for how do you put the squares together, and I can probably fill the rest of my lifetime with this. Anyways, here's the first quilt. I hope that what you see is something shimmering at you, right? And that's because of the light, the way the light and the darks interact in diagonals, and because of the way I've chosen to put the triangles together. So the 4 triangles use exactly the same coloring. And so I put 4 triangles together to make 1 square, and then there's a narrow corner and there's a wider corner, and I alternated them, putting them together. I was challenged by so when I was these were made 2002. Now there's a modern quilting movement that loves to use solids. But back in 2000, it was really hard for me to find solids in Edmonton. And so I was groaning around. I went to the store and said, do you have more solids? And the store owner went, solids are boring. And I go, I don't know what's boring about this. And then I was challenged to make a non-boring quilt with just 3 colors. Okay, so I bought a bolt of black and a bolt of white and a bolt of red, and decided to use exactly the same ordering, the labeling, the A, B, C. Well, then how many ways can you put 3 colors together? 6 ways. You have 3 choices of fabric for A. B has to be a different color, so you only have 2 choices left. Once you've chosen A and B, there's only the 3rd color left for C. So 3 times 2 times 1 is 6. So you have 6 ways to color a triangle. The top row shows the 6 ways, and then the bottom row shows their asymmetrical partners. And then well, how am I going to put those together? So there's different ways of putting these together. So here's one quilt where I've decided to put, so these squares, these are exactly the same, okay? And these are two different ones, either a black background, I call it, or the red background. Anyway, two that are the same, where once you go across, the color changes. Right, so it ends up, you have 6 blocks. 6 blocks that look fundamentally different, and then I made 4 of each, and 4 of each together. So here are 4 the same, but slightly rotated, 4 the same, and then anyways, those were the rules for that particular quilt. Sometimes quilts happen because you've got leftovers, and so this is just willy-nilly. And then here's a different way of putting squares together. So now 2 neighboring triangles have the same back, have the same A, but the B's and the C's are different. Anyway, yeah. It's like, anyways. And then again, you can do 6 different ways of doing that, et cetera, et cetera. And so I call this the Sharp series, and I call this the Blur series. Okay. So now you can kind of see the difference. Right? You can see the scale of these quilts, right? Not giant. Technically, very difficult to put together. There are some evenings that I tried to put 2 triangles together. I'm not satisfied because things are offset a little bit. Rip it apart, put it back together. My limit is 3. Once I've done 3, I put it aside, and I try again the next day. So that doesn't happen a lot, but it happens. So you have to have a lot of patience, and I'm just very, very finicky, very, very particular about how they fit together. So we can, after the talk, I'm happy to hold up the other ones. Okay, just a quick preview of what I'm working on now. So quilters among us will definitely know the log cabin block. You start with a square, and this is the order in which you would build this block. So you start with the square that is labeled 1. You would add a little rectangular piece of a certain dimension, a certain width to it, number 2. Then you can fit number 3. And a log cabin block is typically built up with all of the strips the same width. Well, you can play around with that. What if you didn't do that? What if you used wide and then slightly narrower, et cetera, but in such a way so that in such a way that you maintain squares all the time, or rectangles. These are rectangles. Here, you maintain squares all the time. Okay, so here is a narrow one and a wide. It becomes a little wider, the next bar is a little wider, so that means this one has to be a little bit narrower in order to maintain the square. And these strips are the same width all the time. Okay, and you get this really cool optical effect of these curves in the corners. So I'm just playing around with this concept, and this is the first prototype I've made. I want to make this bigger. I want to make many more bars, right? And at some point, I'm kind of limited by the length or the width of my fabric. But anyways, that's kind of my next series. After all of these triangles, it's time to take a little break from the triangles with the 8 tapered bars. All right, so I've overstayed my welcome. It is now a little bit after 6:15, so I know I have to stop. So here is I think what I've touched on is that you can use mathematical concepts to create quilts, right? In the design or the creation of quilts. I find it immensely satisfying. But we can also recognize mathematical concepts in quilts that could surprise, delight, and hopefully I have surprised you. Hopefully I've inspired you and I've delighted you. I see lots of smiles on faces, so I know that I've delighted many of you. So with that, I will put the poem on again and close my presentation. Thank you for your attention.